YouTube now.
All good, Neil. All good, Neil.
Okay, good evening, everyone. A very warm welcome to the Astronomical Society of Edinburgh's September online meeting. I'm Neil Martin, President of the Society. I'd like to extend an especially warm welcome to our guest speaker for this evening, Professor Jonathan Nichols. And for those joining on Zoom, please can you now ensure that your microphone is muted? Thank you. We've a compact agenda this evening. I'll introduce Professor Nichols formally in a moment for the main talk this evening, and then afterwards I'll highlight just the main items to look forward to in the coming months. So Professor Jonathan Nichols is a reader of planetary auroras in the School of Physics and Astronomy and Director of Research and Enterprise at the University of Leicester. Jonathan gained his degree in physics with space science and technology and his PhD from the University of Leicester before also completing a postdoctoral research associate position there. He then spent time at Boston University in Massachusetts, again in a PDRA post, working on a large Hubble Space Telescope program of observations of Jupiter's and Saturn's ultraviolet auroras. After returning to a similar post at the University of Leicester in 2008, Jonathan was awarded a 5-year Science and Technology Facilities Council Advanced Fellowship in 2011. Jonathan's research background is in the magnetospheres and auroras of the outer planets, along with astrophysical bodies such as exoplanets and brown dwarfs. Jonathan's work encompasses theoretical and data analysis studies, and he's been using the Hubble Space Telescope to study Jupiter's far UV auroras for more than 15 years. He's worked on comparing auroral observations with data from the NASA Juno mission, and most recently has pioneered the James Webb Space Telescope's imaging of Jupiter's H3 plus auroras. Ladies and gentlemen, please welcome Professor Jonathan Nichols.
Thank you very much indeed for that very kind introduction. And so let me share my screen and hopefully we're all away. So thank you very much indeed for the invitation to talk. I am always very happy to talk about Jupiter and its aurora and its magnetic field, but not just Jupiter. There are, in fact, many planets in the solar system and likely across the universe have displays of aurora, and possibly some even more spectacular than the ones that we know about in our solar system. So I usually start by asking the audience who has seen the aurora, and given that I'm talking to the Astronomical Society of Edinburgh, I'm pretty sure that most of you have probably seen the aurora, given that whenever we see news articles saying the aurora might be visible tonight, it's always across Scotland. Those of us unfortunate enough to be in, well, the Midlands in England, generally see it very rarely. So I guess, could you by Zoom put your hand up or something if you've seen the aurora? And then it gives me a good idea. Yes, how many? There are plenty of auroral images in the background there. I can see. Excellent, good. So I'm talking to I'm talking to experts here. Now, you will have all seen the aurora from the ground, and as you will probably know if you've seen it with your eyes, no, it probably doesn't appear quite as green as it does in pictures, and that's because of the way that cameras work. Of course, they record color in faint color much better than our eyes do, and so people tend to be a little bit disappointed sometimes when they do see the aurora. But I always think that it's made up for by the fact if you've got a nice clear sky and you can see the whole display above you, it really does make a spectacular phenomenon. And I saw the aurora in May when we had the last year, the year before, when we had the really large storm. But I've also, that's me just to prove I've seen the auroras in Alaska. That's me looking up at the auroras in Alaska when we had a really wonderful display that night too. So, okay, so you're probably familiar with the auroras from the ground, but you might be less familiar with what the auroras look like from above. And to understand what we see from above, we need to start with where the auroras where the story of the auroras actually begins. And you may be aware that the story begins at the sun. So the sun is obviously our local star, a typical G2V type star in the center of our solar system. And what makes it particularly interesting for us, other than the fact that it gives rise to all life on Earth, is the fact that it's full of magnetic fields. And those magnetic fields are not static. They are always moving around, and this fantastic data here was taken by the Solar Dynamics Observatory, and it's just one example of numerous wonderful videos taken by this spacecraft. When I first saw this video, I thought it was CGI. I thought it was one of these fancy NASA videos that have been put together, but no, it's real data showing you how energy is stored. If I show you again, in these magnetic field lines that are protruding from the sun, and they can suddenly snap, releasing a large, enormous quantity of energy into the space surrounding the sun. Some of this material, which is ionized, called plasma, it falls back down onto the surface of the sun, and you can see the collisions there. But huge blobs of plasma, which are about as heavy as Mount Everest, can be blasted off the surface of the sun in events that we call coronal mass ejections. Now, these form part of a stream of material that's flowing away from the sun at about 1 million miles an hour. It flows that fast because ultimately the sun's atmosphere is extremely hot. It's about 2 million Kelvin, and as we know, hot air rises, and gas at that heat at that temperature rises incredibly fast, even off the surface of the sun, and it reaches those speeds, several hundred kilometers per second, by the time it gets out to Earth. And that material ultimately expands to fill all the space in the solar system, eventually running into interstellar plasma populations way out beyond Neptune and Pluto in a region that we call the termination shock. But when that material hits the different planets, it causes different effects. Now we can zoom out a bit and we can see these the various different wonderful displays of activity on the sun. But this is some really nice examples that show you some of this material coming straight at us, and that there was a great example of what happens when this very energetic, and again there, very energetic particles come off the sun and they hit the camera and they cause all that noise on the camera. And that's the kind of thing that can cause severe space weather at the Earth. So there's a nice cartoon in the next slide, which shows us what is the process that gives rise to the Earth's auroras. Now you might know, that it's this material from the sun that's driving the Earth's auroras. But it's a little bit more complicated than that. It's not just a case of this plasma hitting the Earth's atmosphere or hitting the Earth's magnetic field, and some of these particles getting funneled down to the atmosphere where we can see them. If it was, then I think my field would be a little bit more easy than what it is. It's actually a very, very complex process. And if it was just particles from the sun, then you might wonder, well, why do we see the auroras on the night side? Why are there any auroras on the night side if these particles are coming from the sun? Well, the answer is, of course, that most of the particles that you see causing the aurora actually originate from the Earth's own atmosphere. It's the energy that comes from the sun. And if I run this cartoon again, you get an idea as to the kind of processes that are actually occurring. This material, this flow from the sun, causes the Earth's magnetosphere or magnetic field to be stirred around, going from the day side to the night side and reconfiguring and going back again. And it's this dynamic process of stirring the Earth's magnetic field round, magnetosphere round, that drives it enormous circuits of electric currents that flow around the space surrounding Earth. And where those electric currents have current that's flowing, well, effectively out of the Earth's atmosphere, corresponding to electrons barreling down into the atmosphere, that's when you get the Earth's auroras. And that's why we see an auroral oval surrounding the pole. And it's driven by the solar wind, but it's not directly always caused by the solar wind. And this is the result. So this is what you see if you're in a satellite looking down on top of the Earth's poles. You see the auroral ring surrounding the pole, but it's not static. It's extremely dynamic. It's very variable. Sometimes it's fat, sometimes it's thin, sometimes it's bright, sometimes it's faint. And that variation gives you an indication as to the activity that's going on in the space surrounding the Earth. All the energy from the sun is getting built up in the Earth's tail, and it can suddenly be explosively released in events that we call substorms that give rise to auroral emissions that you see here. And it's when you have the conditions are right that the auroral oval expands, and then this energy is released, and the auroral oval can become extremely large and bright. And so that's the kind of event that drives the Earth's auroras. And so you might imagine, oh, you might wonder, well, the Earth has these fantastic auroras. What about the other planets? Well, it turns out that, yeah, if you have a planet that's got a magnetic field and it's got an atmosphere, then it has auroras. What about Jupiter? So this is my favorite planet for all sorts of reasons. But one of the main reasons is because its magnetosphere, that's the region of space that contains and is controlled by the planet's magnetic field, is extremely large and powerful. It's much bigger than the Earth's. In fact, it's about 5 times bigger than the sun. If you are able to see Jupiter's magnetic field in the sky, next time you're outside with your telescopes and you're looking at Jupiter, imagine a disk the size of the sun plonked on top of Jupiter, and that is Jupiter's magnetic field. So because it's 5 times further away than the sun, its magnetosphere is 5 times bigger than the sun, so it would appear the size of the sun. It actually extends beyond the orbit of Saturn. We know that because of data from the Voyager spacecraft, and it's plausible that Voyager 2 passed by Saturn inside Jupiter's magnetic tail. So this is how big this structure is. And if you have an extremely large and powerful magnetic field, it leads to extremely powerful auroras. So how do we study the auroras? Well, these days we're lucky that we've got the NASA Juno spacecraft there, and the Juno spacecraft is a polar orbiter. So every time it orbits Jupiter, it gets a great view of the down on the poles of the aurora. And it can also measure the particles and the magnetic field associated with these bright auroral emissions. But we can also observe from Earth, and we do that using the Hubble Space Telescope. So why do we need to use the Hubble Space Telescope? Well, this is Jupiter's aurora. This is the northern aurora. We've got the Earth here to scale, so you can see the extent of these features. These are shining very brightly in the far ultraviolet, which is a wavelength that is very strongly attenuated by the Earth's atmosphere. So we have to go above the Earth's atmosphere and use the Hubble Space Telescope, for example, in order to observe these spectacular auroras. So there are a number of features that we can see here, and I'll show you some more details of this later on. But to introduce it, what we've got this ring of aurora surrounding the pole, or the magnetic pole. That's called the main auroral oval, or the main emission. We have a good idea about what causes that, and I'll describe that later. We have these spots and tails coming off them, and those are called the Galilean satellite footprints. So if you follow the magnetic field, if you remember the bar magnets experiment, where you've got iron filings, they make this nice field line structure that you can visualize. If you imagine those iron filings surrounding Jupiter, then if you follow the line of iron filings from this bright spot here on the left, then you'll end up hitting the moon Io. Similarly, Ganymede and Europa, these two spots over here. Callisto has one as well, but it's extremely faint. And these emissions in the polar region are very variable and very transient, and we still don't really have a good idea what causes all of this swirl. It's called swirl emission because it sort of appears to swirl around. Emission going on there. Now, these auroras are they're about 1,000 times brighter than the auroras in our sky. So if you get an idea about what the auroras look like in our atmosphere, these are about 1,000 times brighter. The total power emitted here is several terawatts, which is several nuclear power stations. Right. So what's causing these enormous auroras on Jupiter? Well, there are probably some auroras caused by the sun, but the most of the energy and the most of the dynamics are caused by this little thing here. This is Io. It's my favorite moon, not least because it looks like a pizza, and pizza is my favorite food, but also it is extremely volcanic. The volcanoes on Io liberate sulfur dioxide into space at the rate of about 1 metric ton per second. That's equivalent to having an active comet sitting deep in the magnetic field of Jupiter. And that gives rise to the dynamics that lead to Jupiter's auroras that I'll describe shortly. But you might wonder, why is Io so volcanic? What's causing this little moon to be so volcanic? Well, it's simply tides. The tides on Jupiter are enormously strong. It's pulled by the other Galilean moons, and as Io orbits Jupiter, it experiences tides that heave the surface up and down by 100 meters every time Io orbits. That's tides of solid rock on the surface of 100 meters high. So you can imagine that much movement drives friction inside the moon and heats up the rocks, which is what leads to this volcanism on Io. And this material gets released into space. You can see a great image or movie of one of the volcanoes called Tvashtar that was erupting when the New Horizons spacecraft flew by in 2007. And this material forms donuts of plasma surrounding Jupiter. And it's that, what we call Io plasma torus, that is responsible for the source of plasma that drives the emission that we see on Jupiter. Now these were taken, images were taken in sodium Sodium's very bright, of course, resonates very strongly with sunlight, and so you can see, if you have the right equipment, you can see this material orbiting Jupiter, surrounding and causing this disk of plasma surrounding Jupiter. So what causes Jupiter's auroras? Well, this is an image of auroras, Jupiter's auroras, superimposed on a visible image of Jupiter. And if you want to understand it, then all I have to do is put up this equation here, which no doubt you'll understand. This came from my thesis back in the days, and hopefully that explains everything, and I can take questions now. No? Okay, well, I guess what I'll do is a picture tells, I think, more than 1,000 equations does. And so this is a picture of Jupiter's magnetic field. The white lines are the magnetic field. We've got Io, and we've got this red region, which is this disk of plasma that is released by, or this region of plasma that's released by Io. So why does it go out into a disk like this? Well, it's effectively the opposite of an accretion disk, if you're aware of what happens around black holes and very large astronomical objects like that. You've effectively got this plasma that becomes tied to the magnetic field, and the magnetic field is rotating with the planet, which is once every 10 hours. And so this plasma that's picked up suddenly becomes centrifugally unstable and propelled away from the planet to form this large, vast rotating disk of plasma surrounding Jupiter. As it does so, as it moves away from Jupiter, just as if you're an ice skater is rotating and spinning around on the ice, if she puts her arms out, she slows down. That's because of conservation of angular momentum. And the same thing happens here. As this material moves away from Jupiter, conservation of angular momentum means it slows down, and you end up with a tug of war between this plasma that wants to slow down and Jupiter's atmosphere, which doesn't want to slow down. And Jupiter ultimately imposes its will on this material as it's flowing out, to keep it at least partially rotating by the action of an enormous current system that flows around Jupiter's magnetic field, like the electric current system that I talked about for the Earth. And this is what gives rise to Jupiter's ring of aurora that I showed before. But just to indicate that it's not just a static system, it's very dynamic. Here's a movie from Hubble that we took. Well, this will be when then Juno was approaching, and you can see how variable this feature is. Sometimes it's extremely bright. In fact, it almost saturated the telescope here. And this, at the time, was the most powerful auroras we'd ever observed. We've seen more powerful since, but that was the record at the time. And you can see it's very broken up, and sometimes it's very variable. There are patches that come and go. These are sped up by about a factor of 200, so it's not quite this fast, but you get the idea that it's a very, very dynamic environment, just like on the Earth. So this is the ultraviolet auroras. You can ask if there are auroras in any other wavelengths. Well, yes, there are. There's visible here, and this is on the left, and that's just taken by Galileo, and this is infrared aurora taken from the ground. In fact, well, 3 of these are from the ground. In the infrared, this is about 3.3 microns, and this is another molecule. So the far ultraviolet is H2, molecular hydrogen. This is H3 plus, which is a triatomic hydrogen cation. So it's 3 protons and 2 electrons that can, if it existed in this room, it wouldn't survive for very long, but in Jupiter's upper atmosphere, it can survive for quite a number of seconds, several hundred seconds. So, and as it does so, it can emit very strongly in the infrared, which is what's been observed from the ground. And this bottom right is from Juno. We can do even better with James Webb, as I'll show later on. So can we compare the how do we study this? Well, we study it by comparing, for example, the Hubble data that you can see giving us those wonderful movies there with, for example, Juno data. So on the right-hand side, I'm not going to go into the details, but this was taken as Juno approached Jupiter. And the two panels on the bottom on the right show effectively how strongly the solar wind is blowing. So we were looking to see, do the auroras brighten when the solar wind is blowing stronger or not? And there are lots of details hidden in these figures here. But you know, we inferred that there were some features that did respond and others that didn't. And it was very interesting determining which ones were which, because it wasn't exactly what we thought. And so that's the kind of thing that we did. We can also look at the auroras with Juno itself, and Juno, of course, gets these fantastic views looking down on the planet. These are slightly different because they're built from scans across the planet. It's not just a photograph like Hubble can take. So you've got to interpret these somewhat carefully, but you can see that there are details revealed here that are different to what we see in Hubble. Juno can also observe in the infrared, so it was able to observe the H3 plus aurora, and again reveal details that we've not been able to see from the Earth. So, for example, we saw that the auroral spot from leading to Io is very detailed, with spots behind it that are interleaved. And the tail also splits like this. So there's various different details that we've seen, and people are still scratching their heads about what drives these various different features. Another example of the connection with Juno is that we looked at, for example, how strong the currents are flowing in this system, and related that to the strength of the brightness of the auroras on Jupiter. And you would have thought then, if this hypothesis is correct, if our understanding is correct, there would be a clear link between the two. And when we did this, we saw that there was a very clear link, exactly as our theory suggests, between the brightness of the auroras on the one hand and the amount of current flowing in the magnetic field on the other. So this, to me, tells us that we're on the right track and understanding how this process happens. Okay, so I think that's probably enough about Jupiter. Let's move on to Saturn. So Saturn also has auroras, in some ways similar to Jupiter, and in other ways very different. Saturn is sort of in between Jupiter and the Earth. It's rotationally dominated like Jupiter, but it's very strongly driven by the solar wind as well. So these storms that you can see on these various different images here are driven by the solar wind slamming into Saturn's magnetosphere and reconfiguring the tail very strongly and producing these very dynamic and large auroral storms that you see. These images on the right were also taken with Hubble. The flashing is just due to different filters, but the aurora brightness should be consistent throughout. And you can see again, look how variable it is. Sometimes the auroras are very faint, almost non-existent, and sometimes they're extremely bright. And this is driven strongly by the solar wind. The auroras wobble, as we discovered. This is guaranteed to give you a headache if you look at it for too long. But if you look at the cross in the middle, you'll see that the cross is roughly going up and down like this. And what I've done here is effectively I've stacked a whole bunch of different images from different times together and related them by Saturn's rotational phase. Let's move off that. But what the effect is, effectively, you've got the auroras wobbling backwards and forward across the pole, which is a very interesting phenomenon, given that Saturn's magnetic field is supposed to be very, very, very accurately aligned with the spin axis. So if the magnetic field is aligned with the spin axis, why is the aurora tied to the magnetic axis wobbling backwards and forwards? It's still a question that is not yet fully solved. This is a close view of one of these storms, very dynamic, and you can see this, the features that we see here moving give us an indication as to how the energy is built up in Saturn's tail, and it explosively reconfigures like it does at the Earth and produces extremely bright and variable auroral storms on Saturn. What about Uranus? Does Uranus have auroras? It does. Now, these images were taken on the left by Hubble and on the right by James Webb. So on the left, the Hubble. Now, these were taken by colleague Laurent Lamy in 2012. These are, let me say, they're, for the artist's impression, they're very strongly processed. Pulls out, I mean, he's done a great job of pulling out a signal that are on the limit of detectability. And these blobs here are actually near to where you might imagine the auroras would be on Uranus. So Saturn, Jupiter, and the Earth all have magnetic field, effectively bar magnetic fields that are almost aligned with the spin poles. Uranus is different. Its bar magnet is, well, it's less like a bar magnet, but if you concentrate on the bar magnet bit, it's not aligned with the poles at all. In fact, it's almost very strongly not aligned with the poles. And so as the planet rotates, this bar magnet barrels around, and the way that interacts with the solar wind is simply not well understood. But we might imagine that you would see auroras near the poles of the bar magnet, and that's what we see on in these images here. Now, James Webb, which is exquisitely sensitive, can observe in the H3 plus aurora, and it also saw auroras pretty much near where you expected them to see. It's in the red in these images here. The white thing there, I think, is a cloud. So Uranus does have aurora. We know much less about it because obviously Uranus is much further away, but there's an ongoing programs to observe Uranus and Neptune with James Webb in order to determine more information about the auroras on these enigmatic planets. All right, so moving out in the universe, alien auroras. So we've seen that planets in our solar system, every planet which has a strong magnetic field and a collisionally thick atmosphere has auroras. Would we expect similar processes to occur throughout the universe? Well, I mean, yes, right? All planets that match those conditions will probably have auroras. The question then is, can we detect any? Can we use any information that we got from those kind of processes to tell us something about the characteristics of the planets that we're looking at? Well, people have thought about this in great detail, and there are a number of different ways that you could possibly detect these things. Now, I'm going to say straight away, nobody has seen unambiguous evidence of the auroral activity on an exoplanet. That is a planet orbiting another star. Unambiguous. There's been proposed detections, but and I'll explain how we might do that shortly. But it's still very much an open search. So how might we go about doing this? So we could look for the radio. In the solar system, every planet that emits that has auroras also emits radio. So the Earth does, Saturn does, Jupiter does, Uranus do. These beams all point outwards into space, and they are caused by the electrons as they barrel down the magnetic field. Before they hit the atmosphere and cause it to glow, they emit radio waves out into space. So if you were to look at Jupiter in the radio, you would see it pulsing. as Jupiter rotates once every 10 hours, it's like a lighthouse. You know, like how Saturn's aurora pulsed, and how in that movie that I showed of Jupiter's auroras, the aurora was rotating around. This lighthouse beam of radio is also beaming around the solar system from Jupiter. That's one way that we might be able to detect exoplanets. What about star-planet interactions? This is the signature of the magnetic or the interaction between the planet and the star, mediated along magnetic field lines that perhaps cause bright spots on the surface of the star that might be tied to the orbital period of the planet. What about if there is material that is piled up in front of a very rapidly orbiting planet as it plows through the star's environment? Could it snow plow material ahead of it, which could then absorb light from the star, and then you could see a dip in the light as this ahead of the planet in its transit across the star? Or what about direct UV or infrared emissions from these objects? Well, all of these have been proposed and discussed at length, and as I say, nothing has as yet unambiguously determined the existence of auroras on another on an exoplanet. But there have been interesting detections, and I'll talk about that very shortly. So this was an example of one of what we thought might happen with a hot Jupiter orbiting a star. If I run this is a hydrodynamic simulation of a planet with a magnetic field that is orbiting its star. And as you can see, it's snow plowing this material ahead of it as it's orbiting around. And if you effectively count up the number of particles between the star and the observer out here, you end up with effectively an asymmetric transit that looks like this. And when we compare it with again UV, near UV this time, observations of this particular planet was WASP 12b, there is some kind of suggestion possibly that there's increased absorption ahead of the planet, but we weren't particularly convinced. The problem here was that the detector that we used on Hubble had been deteriorating, and the dark, effectively the noise in the background was too high for us to make any concrete statements. However, I think the biggest problem for this is when we were doing this work, we also then actually calculated what the opacity would have to be of this material, and it's much too high for what you would expect. So I actually think that this, even though many people have thought about this in detail, I actually think this is probably the least, and we've worked on this and we've looked for it, it's probably the least promising method of detection. So what about other methods? Well, I think probably the most promising method is the radio. Why? Well, in our solar system, there are effectively, if you were to look at our solar system in radio eyes, if you didn't see in the optical, but you saw in the radio, you would see two objects. One is the sun and the other is Jupiter. And Jupiter is, surprisingly enough, as bright as the sun when it's quiet. Okay, surprisingly enough. And it can even be brighter. We're talking about low frequency wavelengths here. So this is 10 megahertz or so. This is anything below this dotted line you can't see on the Earth, because it gets absorbed by our own ionosphere, which is the thing that the rest of my research group study for the Earth. But if you're in the solar system, then you can see, of course, all of these emissions. And Jupiter is really that bright, and its radio emissions are also very distinct, very different to the sun's. The sun's is incoherent emission that's coming at you it's not polarized, it's just coming at you all the time. Sometimes it's bursty, sometimes it's not. Jupiter's radio emission is very strongly circularly polarized, so you can immediately pick it out. It's it has what we call a very high brightness temperature, which just means that it's very powerful. It would have to, if the radio was emitted by something that is just hot, then it would have to have an extremely high temperature to be emitting this powerfully, these wavelengths. And it beams. It's beamed, as I said before, as Jupiter rotates around, this thing is pulsing at you. So Jupiter is a pulsar in our solar system. It acts just like a pulsar, pulsing radio at us. So very distinctive radio emissions, and I think that that is the best reason why we should be using radio to observe these other planets. The reason why Jupiter's radio is very intense is because radio emissions, the strength of radio emissions, are not determined by the temperature of the object, but it's determined by the strength of the magnetic field. And Jupiter has a very powerful magnetic field. So if you have something that has a very powerful magnetic field, then it could in principle have very powerful radio emissions. And back in the day, I did some calculations as to the kind of object that you would need to have in order to be detectable. And I looked at Jupiter-like planets. I've got Jupiter with Popeye here. You know, if Jupiter ate its spinach and became extremely strong and powerful, it was very massive, it was rotating very rapidly, it was quite distant from its star, then it could potentially be detectable with even LOFAR, which is currently operating, and there are possible detections. And other radio telescopes like SKA coming down the line in several years. And the interesting thing about this is that if I plot the number of confirmed planets versus radial distance from their star, there's not many out here in this is in AU, this is 10 out here and further out. So this is the outer solar system regions. And we're not very good at detecting planets that far out because they don't have very strong Doppler shift effects on the planet and various other things. And so this is potentially a way of accessing those planets which are further out in the solar system or in their stellar systems. Why do I also think radio is a good way of detecting exoplanets? Well, it's because it's already been seen on objects that are slightly bigger. Objects that are slightly bigger than planets, in between planets and sort of lower mass stars in terms of mass, are called ultra cool dwarfs, and consisting of brown dwarfs and various other types. So these are some nice artist impressions of ultra cool dwarfs. We've got Jupiter. A planet is a planet up until about 13 Jovian masses. A brown dwarf is typically about 13 to 80 Jovian masses, and then you've got the very cool M dwarfs sitting around 80 Jovian masses. Now, some of these have been seen to emit radio, very like Jupiter's auroral radio emissions. And this is a great example here. This is TVLM 513, and it's peaking, spiking at us, pulsing like this. Very strongly circularly polarized emission. It looks to me like auroral radio emission. Now, from a planet's perspective, I'm coming at this from a planetary perspective. I look at these objects like very big planets. Many of my astronomer colleagues look at them as being small stars, and that's where we slightly disagree. But I think that we are looking at, we've made some theoretical arguments to explain why we see the brightnesses that we see, and we've done a reasonable job. And there are more and more of these being discovered every day. There's about 20 or 30 of these that have now been discovered. So there's Jupiter-like processes that we've inferred, just like I've talked about for Jupiter, but also similar to how Io interacts with Jupiter. You could imagine that there is an interaction along the star's magnetic field line, which is the black line here. And again, you can make calculations. I'm not going to go into the details, but you can make calculations as to how bright the radio emission is from these things. And indeed, some of these have been detected And so I think that we've seen Jupiter's radio emissions, we've seen brown dwarf radio emissions, and so we've now got to just work out towards the middle, which is potentially sort of the large exoplanet radio emissions. What about direct observations? Nothing from exoplanets, but the best observations that I've seen in the literature so far have been James Webb observations of a brown dwarf, and this is a spectrum of intensity in the infrared that was observed from one of these things, and you can see that there is an enhanced emission here in a region where you have methane lines. So the possibility is that this is methane being excited by electrons hitting the methane in the atmosphere of these brown dwarfs, causing the methane to glow like it does, like the hydrogen does on Jupiter and the oxygen and the nitrogen does on Earth. Possibly, I think it's very exciting, and that's a region of active research. And this is a nice artist's impression that went with the press release to give you an idea as to the kind of thing it would be. Okay, so I'm just going to end just by showing you some of my favorite observations from James Webb, which is my own observations, obviously, but it's not just that, because it just shows how amazing Jupiter's auroras are. So we've seen Jupiter's auroras there with the ultraviolet, gives you an idea of how dynamic they are in the ultraviolet. But as you know, we can observe the auroras in the infrared. Can James Webb observe Jupiter's auroras? It was thought not, because Jupiter is very big, very bright, very variable, exactly not the kind of thing that James Webb was designed for. Figured out how to do it, and this is the result. This is James Webb observations of Jupiter's infrared auroras that was obtained on Christmas Day in 2023. I waited until Boxing Day before I opened the email to determine whether I'd broken James Webb. Turned out I hadn't, and these were this was the result. It was the best Christmas present I could have asked for. We've seen new features that we've never seen before. We've seen we had Hubble observations as well, so we were able to compare the brightness of the infrared with the UV, which tells us about the energetics of the auroras. And I've been studying these ever since. We've got I've got a postdoc who's about to start working on these, and we've got more observations in the pipeline. So it's a very exciting time to be studying Jupiter's auroras. The future's bright. We've got JUICE on the way. It will get there sometime in the 2030s. Can't remember the exact date, but it will get there and study the auroras in a way that we've not been able to see before. That's going to be extremely exciting. A European mission to Jupiter, Ganymede, and that's going to reveal many different processes that we've not been able to see before. I'd love to see an ice giant mission to Uranus and Neptune. The political winds are not blowing in the right direction from that right now, but let's keep our fingers crossed. Hab Worlds is still being talked about. This is going to be the next big observatory, great observatory that would be able to, if we had our way, it would be able to observe in the ultraviolet and the infrared at the same time. It would be able to resolve features that we've not been able to see before. It would be a wonderful instrument, and I really hope that keeps going, and the momentum behind that project keeps going, and we see this tremendous observatory down the line. And with that, thank you very much.
Well, thank you very much indeed, Jonathan. Can we all come off mute and thank Professor Nichols in the usual way? Fascinating talk, and we know, as you said earlier, when auroras are likely, it makes the 10 o'clock news. So getting outside and observing them with the naked eye or with cameras and stuff. Hard enough, even up here in the north of Scotland. So observing these phenomena in the solar system and beyond, it's incredible. There's so much stuff out there. So thank you again. Ramsey, are you able to handle the questions on chat, or will I do that?
Yeah, we've got one. Can you hear me?
Yeah, got you.
Okay, sorry, I had to duck out and reboot and start again. There's one question from chat from Nigel. Nigel, do you want to ask your question?
Yes, thanks very much, Ramsey. Jonathan, thank you very much indeed for your talk this evening. Absolutely fantastic. And before I ask my question, I think I would just like to congratulate you on your slides. They're probably the best slides I've ever seen in terms of getting across your subject. They're absolutely fantastic presentation. So thank you very much for that. I was just wondering. Whether with the exoplanets, whether the class of star will have an effect on the auroras that are seen in exoplanets. Whether that has an effect on it. Obviously, we get different auroras for different planets in our own solar system, but that's just for our class of star. Does the class of star have an effect at all?
Yes, that's a very well. Thank you. First of all, thank you very much for your comments. Very, very kind. Yes, absolutely. So the Earth's auroras are affected by the activity of the star, of our star. When the sun is at its maximum intensity, maximum activity, that's when we see the most aurora. And it would be the same with exoplanets. So we think that any star which has a very active corona, and surprisingly enough, the most active coronas are M dwarfs, which even though they're really small, puny stars, actually are extremely variable and have very variable UV light curves, and that's because they have extremely large flares on them. So we think that a star like that, like an M dwarf, is probably going to have a very strong space weather impact on the exoplanets. Now, the difficulty with then observing the radio emission from that kind of exoplanet is because then you've got a very noisy background. You're searching for a very faint signal in a very noisy background. Mm-hmm. So we actually don't like looking for auroras around M dwarfs because of that very reason. Most of the radio surveys that I've seen have been looking for planets around sort of sun-like stars. In fact, most G stars are more active than our sun. Our sun, for some reason, is about 100 times less active than a lot of similar type stars. I'm not really sure people know why, but most stars are more active than the sun. And so we tend to focus on slightly larger stars that have stronger solar winds, but are less sort of crazy.
Yeah. Thank you. That's great. Thank you very much.
No problem.
That's it. No more questions. And thanks very much for your talk. As you can see, I'm a bit of a aurora geek myself.
Jim Barron has a question.
Hi, Jonathan. Thanks very much for the talk. Very interesting. You talked about the pulsation of from Jupiter, the radio waves tied into the rotation. I was just wondering, are the radio emissions, are the strengths dependent on the difference between the magnetic and rotational axis, or does that just affect the strength of the pulses?
Yeah, that's a really good question as well. It does affect the strength of the pulses. Yes. It doesn't affect the overall intensity of the emission because that comes from the processes that I talked about with IO and etc. But the intensity that you see at any one time is very strongly related to the tilt. So you will either see nothing or a lot if you're in the beam or otherwise. So yes, it does affect it. And in fact, you can observe Jupiter's auroras yourself if you were to. You can build a radio telescope. There's a project called Radio Jove, which tells you how to do that. You need to be in a radio quiet area. But you can build, it's possible to do. We've got one, we had one on the roof of the physics building in Leicester. Obviously you're in the middle of a city, so there's lots of noise from ambulances and various other things going past. But you can observe this yourself, and it's strongly tied to where Io is in its phase around Jupiter, the rotational phase of Jupiter, but also how strongly the solar wind is blowing. So you see various different features, different types of bursts, based on those three criteria. So yeah, it's fascinating. And don't ask me about the physics, because the physics of it is incredibly nasty. And I'd rather stay out of it if I can. But it's a really strong tracer of the activity in Jupiter's magnetic field.
Thank you.
I think we've got another question from Marius and Chia. So the question was, are there more aurora in the outer solar system than the inner? And is there a relationship?
Yeah, that's my question there. Yeah, I was just wondering, because I think most of the examples you have there were like Jupiter and Saturn, and I kind of wondered,
Yes.
what the relationship is.
Again, very good question. So the answer is yes. Mainly because the strengths of the magnetic fields of the outer planets is much larger than that of the inner planets. Of the inner planets, only the Earth has a global magnetic field. Venus has none. Mars has some crustal bits of remnants of field, and actually there are auroras associated with that. Perhaps it was unfair of me to leave poor old Mars out. It does have some very strange looking sinusoidal auroral features. Those have only been discovered very recently, in fact. So yeah, Mars does have some auroras. Venus, not really, because it doesn't have a magnetic field. It interacts with the solar wind in a very different way. Mercury is an interesting one. Mercury has a magnetic field, but no atmosphere. So what do we see at Mercury? We see X-rays coming from the surface of Mercury around basically where you would expect aurora to be. So that is, we think, an auroral-like feature that is coming from the surface. A bit different in terms of how it actually is caused, but that is something that the Bepi-Colombo spacecraft with the MIX X-ray instrument that was built at Leicester is going to study, and that's on its way to Mercury right now. And that's one of the things that my colleagues at Space Park will be looking at and trying to figure out exactly what's going on at Mercury. If Mercury had an atmosphere, it would have very strong auroras because it's very strongly driven by the solar wind, and that would lead to a very strong auroral emissions. So it's not that being closer to the star means you have weaker auroras. It's literally just, well, I suppose the further you're out, the bigger the more material there was in the proto-nebula for planetary nebula for those planets to get bigger, and bigger planets have bigger magnetic fields and therefore stronger auroras.
Can I just ask something on that? Is the X-ray emission from Mercury caused by bremsstrahlung?
No, it's caused by fluorescence from the surface.
Okay.
It's not Bremsstrahlung. In fact, we see Bremsstrahlung from Jupiter.
Oh, right. Okay.
As this, like as the aurora, the electrons produce radio waves, ions traveling down the magnetic field produce Bremsstrahlung and very strong X-ray emissions from Jupiter.
Mhm.
It's not that from Mercury. It is fluorescence, X-ray fluorescence from the surface. So particles, molecules that are energized into a higher state, and they emit X-rays later on.
Thanks.
All right.
Thank you. Great talk.
Great stuff. Thanks, everyone. I think that brings us to the end of the questions on Zoom. Will, do we have any questions from our YouTube audience?
Yep, we have a couple of questions have come up. First of all, I'd like to say a fantastic talk, and it's been very well taken by our followers on YouTube with some good viewing. So excellent stuff, Jonathan. Thank you. First of all, it's not directly about the aurora, but it's about the magnetic fields. We have a question from James Christopher Hunt, who asks, Uranus's and Neptune's magnetic fields are so bizarre, off-center and misaligned. Is it possibly because they have large amounts of water accepting their mantles to help create a dynamo effect? And I suppose he's just wondering about why their magnetic fields are misaligned, as it were.
Yeah, again, really good question. So the dynamos that are driving the magnetic fields are if we talk about Jupiter, first of all, it's generated deep in the interior. Jupiter is very strongly rotating, very rapidly rotating, and it's made predominantly of hydrogen. And the convection cells deep within Jupiter are obviously very strongly aligned because of a strong Coriolis force that aligns these convection cells and produces a nice strong dynamo. Same with Saturn. But it's not a perfect dipole. It's actually slightly lumpy. And that lumpiness is caused by smaller flows interior to the planet that are occurring nearer to the surface. And that is just literally due to variation within the planet. Little bits of the planet are perhaps moving one way, and other bits are moving another way. And because they're slightly electrically conducting, they produce distortions in the magnetic field. The same thing happens at Uranus and Neptune. Those planets are predominantly they're hydrogen, but with a substantial water and methane atmospheres. And those are able to obviously produce conductivity higher up in the atmosphere, within the mantle, that is able to distort the magnetic field, the global magnetic field, in such a way to produce very strange magnetic fields. The reason why it's tilted over quite so much, I'm not entirely sure about. I suspect it may be due to the reason why the planets are tilted over in the first place, which people think is possibly due to collisions back in their early history. It may have knocked the flows around in the interior. It's a good question, and one that I will go back to and have a look at, read my undergraduate textbooks to find out what's going on there. But yeah, hopefully that helps a bit.
Marvelous, thank you. And I've got our second and final question from YouTube is from Martin Pride. And you've already sort of alluded about the development of the planets outside, towards the bigger planets and the magnetic properties, magnetic fields of the planets. But he also asks, does the intensity of the aurora depend on the mass of the solar wind or the speed of the solar wind, as well as the properties of the planet?
Wow, these are some of the best quality questions I've had in a long time. So it depends more strongly on the speed. And the reason for that is because it's Well, there's two things that affect it. It's mainly the speed and the strength and direction of the magnetic field. Why is it mainly the speed? It's because it's the momentum flow and effectively the dynamic pressure on the front of the magnetosphere the equation for that is the mass density times the velocity squared. So the velocity has more of an effect than the mass density. The second thing is the magnetic field. It's the magnetic field, so that's the energy that drives the auroras. It's the magnetic field is the switch that determines whether that energy can be diverted to the Earth or not. So if the magnetic field is strong, then that means that more of the energy can be dumped into the Earth. But also if the magnetic field at the Earth, if this magnetic field in the interplanetary space near the Earth is pointed northward, we won't get much of a response. But if the magnetic field is instead pointed southward, in the opposite direction to the Earth's magnetic field in space, then the two magnetic fields can come together and merge and reconfigure in that way that drives the system in that cartoon that I saw before. Okay, so the two important things are the speed of the solar wind and the direction and strength of the magnetic field that's carried with it.
Excellent. Thank you. Thank you very much. It's all from our viewers on YouTube.
Excellent. Thank you, Will. Well, let's again thank Jonathan for his talk and for answering all of our questions this evening. Thank you.
You're very welcome.
Thank you.
Okay, I'll take over the screen sharing again and just finish off the evening with a look ahead to what we've got coming up in the next couple of months. So getting towards the end of September now, and we have a couple of events left this month. The final weekend of the month, we have two doors open events, one on the 27th of September at the Collective Gallery on Calton Hill, and on both the 27th and 28th of September, the doors open event at the Royal Observatory of Edinburgh at Blackford Hill. Moving into October, just to highlight our main meetings, on Friday the 3rd at Augustine United Church and also online, the two comets 29P Schwarzmann-Wachmann and 12P Pons-Brooks behave like no other. In what way and why? Well, Dr. Richard Miles will describe how, thanks to contributions from amateurs around the world, we now have answers to these questions. So tune in or attend in person to hear about that. And this time next month, Friday the 17th, our online meeting. Our guest speaker is Professor Claudia de Ram from Imperial College London, talking about gravity. It's the overarching miracle that connects everything we know and the reason the universe itself can even exist and evolve. So join Claudia to hear about this journey as we push the limits of knowledge and navigate through the foundations of space-time. Also in October, the first weekend in October at AUC, we're hosting the joint BAA Comet and Meteor section. Incredible collection of speakers at that event, including our own Douglas Heggie. Full details, including how to book tickets, are available on our website. And finally, moving into November, our main meetings in November are Friday the 7th, again, our AUC hybrid meeting. Professor Paul Cook will be presenting a talk on the subject of star formation, and precise details of that title will be confirmed soon. And then our online meeting mid-month, Dr. Darrell Seligman will review the current state of our knowledge of the third macroscopic interstellar object discovered passing through the solar system. That's 3I Atlas, and that was discovered in July this year by the Atlas survey in Hawaii. So join Dr. Seligman in November to hear about our interstellar visitors. Nothing else planned in other events for November, but keep watching this space. And that brings us to the end of this evening's agenda. So thank you for joining us. I wish you all a good night and, of course, clear skies. Thank you very much.
Thank you.
Thanks,
Good
everybody.
night.
Thanks, everyone.
Thank you. Good
Thank
night.
you.
Thanks all.
Folks.
Cheers, Neil. And all excellent.
Other maps you can sit on.